Lesson: Semi-supervised learning in cyber defense. Semi-supervised learning represents a critical innovation in cybersecurity, particularly in addressing the growing complexity and sophistication of cyber threats. This learning paradigm harnesses both labeled and unlabeled data, making it highly efficient in environments where labeled data is scarce, but unlabeled data is abundant. The application of semi-supervised learning in cyber defense leverages the strengths of both supervised and unsupervised learning, providing a balanced approach to threat detection and mitigation. Cybersecurity has become increasingly challenging due to the vast amount of data generated and the sophisticated nature of cyber threats. Traditional supervised learning methods rely heavily on labeled data to train models, which is often limited and expensive to obtain. On the other hand, unsupervised learning methods, which do not require labeled data, struggle to achieve the same level of accuracy and reliability. Semi-supervised learning bridges this gap by utilizing a small amount of labeled data to guide the learning process while exploiting a larger pool of unlabeled data to improve model performance. The efficacy of semi-supervised learning in cybersecurity can be exemplified through its application in anomaly detection. Anomaly detection is crucial for identifying unusual patterns that may indicate cyber threats such as intrusions, malware, and fraud. By integrating labeled data of known attacks with a vast amount of normal behavior data, semi-supervised models can learn to distinguish between benign and malicious activities more effectively than purely supervised or unsupervised models. A pertinent example of semi-supervised learning in action is its use in network intrusion detection systems. Traditional NIDS rely on signature-based methods, which are limited to detecting known threats and are ineffective against novel attacks. Machine learning-based NIDS, particularly those employing semi-supervised techniques, can adapt to evolving threats by learning from both historical attack data and real-time network traffic. This adaptive capability significantly enhances the system's ability to detect zero-day exploits and other sophisticated attacks. Moreover, the semi-supervised approach proves advantageous in the realm of malware detection. Malware classification traditionally depends on a comprehensive database of labeled malware samples, which is challenging to maintain given the rapid emergence of new malware variants. Semi-supervised learning models can mitigate this issue by leveraging a small set of labeled malware samples along with a large corpus of unlabeled data from various sources, such as executable files and network logs. This integration allows the models to generalize better and detect previously unseen malware strains. Phishing detection also benefits significantly from semi-supervised learning. Phishing attacks, which aim to deceive users into divulging sensitive information, are constantly evolving. Labeled phishing data is often outdated or insufficient to train robust detection models. Semi-supervised learning algorithms can enhance phishing detection by using a small labeled dataset of known phishing emails and websites, combined with a vast amount of unlabeled data collected from email traffic and web browsing activities. This approach enables the detection of new and sophisticated phishing attempts that traditional methods might miss. The advantages of semi-supervised learning extend to improving the accuracy and efficiency of user authentication systems. User authentication, a fundamental aspect of cybersecurity, involves verifying the identity of users to prevent unauthorized access. Behavioral biometrics, such as keystroke dynamics and mouse movements, are increasingly being used for continuous authentication. However, obtaining labeled data for these behaviors can be challenging. Semi-supervised learning models can learn from a limited set of labeled behavioral data and a more extensive collection of unlabeled data, enhancing the accuracy and robustness of authentication systems. Despite its numerous advantages, semi-supervised learning in cyber defense is not without challenges. One significant challenge is the quality and representativeness of the unlabeled data. If the unlabeled data is not representative of the actual data distribution, the model's performance can degrade. Additionally, semi-supervised learning models are susceptible to overfitting, particularly when the labeled data is sparse. Therefore, careful consideration must be given to the selection and pre-processing of both labeled and unlabeled data to ensure the model's robustness and generalizability. The computational complexity of semi-supervised learning algorithms is another critical consideration. These algorithms often require more computational resources than their supervised or unsupervised counterparts due to the additional processing of unlabeled data. However, advancements in computing power and the development of more efficient algorithms are gradually mitigating this issue, making semi-supervised learning increasingly feasible for real-time cyber defense applications. Furthermore, the interpretability of semi-supervised learning models is a crucial aspect, particularly in cybersecurity, where understanding the rationale behind a model's decision is essential for trust and accountability. Efforts are being made to develop more interpretable semi-supervised learning models, enabling cybersecurity professionals to gain insights into the model's decision-making process and make informed decisions based on the model's outputs. In conclusion, semi-supervised learning holds significant potential for enhancing cyber defense by leveraging both labeled and unlabeled data to improve model performance and adaptability. Its application in areas such as anomaly detection, network intrusion detection, malware classification, phishing detection, and user authentication demonstrates its versatility and effectiveness in addressing various cybersecurity challenges. However, careful consideration must be given to the quality and representativeness of the data, computational complexity, and model interpretability to fully harness the benefits of this learning paradigm. As advancements in semi-supervised learning techniques continue, they are poised to play an increasingly vital role in safeguarding digital infrastructures against evolving cyber threats.